Hey everyone, so this is the solution video to worksheet 4.3. We're going to be talking about solving equations that involve rational functions and inequalities that involve rational functions. So in this first one we've got an equation that involves rational functions, and in general this is a good sort of procedure to abide by when you're dealing with equations like this. The first thing that I'd probably suggest is check for any restrictions. So check for restrictions on x. Now in this case, if we look that in this first term x can't be equal to -3, in this second term x could not be equal to +3, and in this last one x could not be equal to plus or minus 3. So we're going to want to exclude both positive and -3 from this possible set of solutions. So we note that x cannot be equal to plus or minus 3 for this particular one, and we're going to take care of that. Okay, so we check for our restriction on x, and now we can go ahead and we can move on to the next step. In beginning to solve this equation, we're going to want to find a least common denominator. So find the least common denominator. And from here on out, I'm just going to refer to this as the LCD. The least common denominator is essentially a denominator where if we were to look at each of the denominators of the individual terms, that they would all divide into it, and there wouldn't be anything extra. So that's sort of in the least terms, the smallest denominator we could have where each of the other denominators will divide into it. So one way we can go about constructing this is just to start multiplying denominators together, making sure that we're not doing anything extra that's not necessary. So the first denominator is x plus 3. So we'll just take x plus 3. That's our first factor. So clearly x plus 3 will divide into this LCD. Now we want x minus 3 to divide into it, so we're going to add x minus 3 as a factor of the LCD. So now both of these two denominators will divide into our LCD. So the last one is the x squared plus 9. Well, it turns out we don't have to add that as another factor because x squared minus 9 is x plus 3 times x minus 3. So it's already the case that x squared minus 9 divides into what we have as the least common denominator so far. So we're actually done at this point. And the product of x plus 3 and x minus 3, we'll just go ahead and we'll count that as our LCD. So once we've found the LCD, our third step in solving for x, because that is what we're trying to do here, is to go ahead and we're going to multiply both sides by the LCD. So if there's more than two terms here, we're going to need to make sure that we multiply every single term in this equation by our least common denominator. So here's how we would go ahead and do this. So we've got our LCD, and you don't necessarily need to show this step in your work, but it's good to at least see it the first time. So I'm going to take x plus 3 times x minus 3, and I'm going to multiply that by our first term, which was 1 divided by x plus 3. And we're going to repeat this process for each term. So now we take our LCD again, which is x plus 3 times x minus 3, and we multiply this by our second term, which is 1 divided by x minus 3. We're going to take our LCD, which is x plus 3 times x minus 3, and we will now multiply this by our last term, which was x squared minus 3 divided by x squared minus 9. Now, inevitably what's going to happen here is that things are going to begin to cancel out. So let's see what we can do here. So in this first grouping, the x plus 3's are going to cancel out. Here, the x minus 3's will cancel out. And since x plus 3 times x minus 3 is the same thing as x squared minus 9, these are going to both cancel out. And if we look at what we have left, we've got x minus 3 times 1 plus x plus 3 times 1 is equal to x squared minus 3. And now we've got an equation, no denominators. We can solve this relatively easily depending on what we got. In this case, we're going to end up with a quadratic. So we go ahead, we multiply this all out, we combine like terms and get everything to one side. So let's do that next. So if we distribute the 1, we get x minus 3 plus x plus 3 is equal to x squared minus 3. So the minus 3 and the plus 3 cancel out, and we've got 2x is equal to x squared minus 3. And if we subtract 2x from both sides, we end up with 0 is equal to x squared minus 2x minus 3. I'm going to go ahead and bring that up here now. So again, we've got a quadratic here. I'm just going to flip this. We could use a quadratic formula if we need to. This one actually factors pretty nicely. We can have this as x minus 3 times x plus 1 is equal to 0. So this gives us two possible solutions. One is that x minus 3 could be equal to 0, which implies that x could be equal to 3. Or if we take the x plus 1, set that equal to 0, we get another solution, x is equal to negative 1. Now at this point, you should sort of get an uneasy feeling in your stomach, because one of these solutions, namely the x equals 3, is actually a restriction. So at this point, this is where that be sure to check for extraneous solutions comes in. This is one of our restrictions. So we're actually going to cut that out because we can't use x equals positive 3. So our only solution to this equation that we started off with is going to be x equals negative 1. So this is a general procedure that you can use for any equation that involves rational functions. Just again, make sure you check your restrictions. Okay, so for this next one, we've got an actual inequality that involves a rational function that we're going to need to solve. And in order to do this, the first thing that we're going to want to check is we'd like to get 0 one side. So get 0 on one side of the inequality. In this particular case, we're in good shape already, so we can kind of move on. Step 2, we're going to want to identify any x-intercepts or vertical asymptotes. And we're going to see in a second why we want to do this. Now remember, x-intercepts are zeros of the numerator, and vertical asymptotes are zeros of the simplified denominator. So we're going to go ahead and we're going to do that. So for x-intercepts, we're going to take our numerator, simplified, which is 1, set it equal to 0, and we quickly see that there's no solution here. So this just tells us that there are no x-intercepts. And that's okay. Then we're going to go ahead and we're going to find our vertical asymptotes if they exist. And we do this by taking the simplified denominator, in this case x plus 2. We set that equal to 0, and we solve. Here we see that we have a vertical asymptote at x is equal to negative 2. All right. So in the third step that we're going to do here is we're going to take these points and construct a sine diagram. Very much like the sine charts we made in section 4.2's worksheet. Construct an sine diagram. How about we just construct a sine diagram? That works a little better. Okay, so the way we'll get started with this by taking our real number line, and this is going to go from positive infinity to negative infinity. And on this sine diagram, we're going to mark the x-intercepts and the vertical asymptotes. So that's why we found those in step 2. In this case, we've only got one thing to plop down, which is the negative 2. I'm going to make a note of what this actually is, and that this is a vertical asymptote. So our function actually doesn't exist there, but it is definitely a marker that we want to use. So now we're going to go ahead and we're going to test points. I'm going to go ahead and pick -10 from here, and I'm going to pick 0 from this interval. Now if we go back to the original inequality, once we've got one function on one side and 0 on the other, this is going to be sort of our f of x. This is going to be the function we're evaluating. And in this particular case, what we're being asked is, when is our function f of x greater than 0, meaning positive, or equal to 0? So those are the questions that we're gonna ask ourselves, and we're gonna do this. We're gonna get this solution from our sign diagram. So now we're gonna go ahead and we take our f of x. So in this case, f of x is equal to 1 over x plus 2, and we're going to check these test points. So we're going to first find f of -10, and as before, we're really just interested in the sign here, whether this is going to be a positive or a negative number. So if we plugged in -10, we're going to have a positive number up top because it's +1, and we're going to have a negative number down below, which means that this is going to result in a negative term, which means that our function is going to be negative on this entire interval from -infinity to -2. And then if we pick 0, then we plug that in, we've got a positive number up top. We plug in 0, we're going to have a positive number below, and that's going to give us a positive interval. So our function is going to be positive on this interval, or greater than 0. So now this fourth step is, let's go ahead and solve. Actually, let's use a different term here. Rather than solve the inequality, let's interpret. So interpret the inequality. Now we were asked, when is this function greater than 0 or equal to 0? Well, nowhere is it equal to 0 because there were no x-intercepts, so we don't have to worry about that. We want to find out when it's greater than 0. Well, it's going to be greater than 0 on this interval where it's positive. So we can't include -2 because the function is undefined there because it's a vertical asymptote. But all of these values we are going to include all the way up to positive infinity. So if we interpret the inequality, our solution is going to be from -2 to positive infinity. And that's our answer there. So on this particular interval, this function 1 divided by x plus 2 is going to be greater than or equal to 0 for all values on that interval. Okay, so we're going to kind of repeat the process here in number 3. So step 1. Let's go ahead and make sure that it's 0 on one side. We're being nice here. All of these are already done for you. Okay, so step 2, we want to find x-intercepts and vertical asymptotes. So x-intercepts, we're going to take the top, x minus 3, set it equal to 0, and what we end up with is x is equal to 3. So there's one of our x-intercepts, and if we take the denominator, x plus 2, set it equal to 0, this is going to give us our vertical asymptote. So we're going to have a vertical asymptote at x equals -2. And again, we're going to use these two values to sort of construct our sign diagram. So step 3, let's go ahead and do that. So we're going to make our sign diagram. And we will get our real number line going on here. Once you do a few of these become actually not nearly as obnoxious as they may seem right now. But we're going to go ahead and we're going to plot our points. So we've got 3. Now remember, 3 is an x-intercept, so this is a 0 of our function. So I'm going to mark that as a 0. And then for -2, this is a vertical asymptote. Again, the authors will use the interrobang sign for these, whatever works for you. So those are the only 2 points that we're going to mark. Now we pick our test points. So I'm going to pick -100, just because it's a big negative number, 0, and then +100 from this interval. Also remember that this guy right here, this is going to be our function, our f of x. And what we're trying to determine is find out when is f of x less than 0 or negative. Strictly negative. That's what this inequality is asking us to determine. So let's go ahead and do that. We're going to take our function, which is x minus 3 over x plus 2, and we're going to evaluate this at our test points. So f of -100, again, we're just interested in if this is going to be positive or negative. So if we plugged -100 at the top, we'd have a negative number. If we plugged -100 in the denominator, we'd get a negative number. The result would be a positive value. So our function is going to be positive on this first interval. Repeat the process. We plug in our second test point, 0. That's going to give us a negative number up top. It's going to give us a positive number in the bottom, which will result in this expression being negative, because a negative divided by a positive is going to be a negative. So our function is negative over that entire interval from -2 to 3. Lastly, we'll plug in 100 for our function, and we get a positive number divided by a positive number, which tells us that on this interval our function is going to be positive, or above the x-axis if we wanted to think about it graphically. Okay, now we want to know when is f of x strictly negative. So that means we don't want to include zeros. So I'm going to put an open dot over 3. If this was less than or equal to, we would absolutely include 3. We will never include -2 because that's a vertical asymptote. Our function isn't defined there. And if we're trying to find out when it's negative, well, it's on this interval in between these 2 points. So in step 4, where we interpret our inequality, we've determined that our inequality is asking us to find this interval from -2, not including -2, to 3, not including 3. And that would be our solution interval. Okay, so that should do it for this worksheet, and I will see you guys next time.